the questions being recorded. Sometimes the volume level between the questions and me is a little weird, so we'll just, I'll hopefully end a little early, and then we can have questions. Okay, so like I said, I'll try to end a little early, and then we'll have a question and answer session at the end. So what's for today? Oh yes, I had to make sure I got the. Yeah, there we go. I got the light on so you can see. So what is what's the plan for today? So first, what I want to do is just finish up one or two things that I was going to mention at the last lecture about the solution to the Bloch equation, and then today we'll just talk about how do we get that solution. Why is that a solution to the differential equation? And like I've said in previous years, this is I had differential equations textbooks. Of course, I never looked at them, never opened them, and so a couple of years ago I said, well, maybe I should just read page 1. So this is literally page 1 of the differential equations textbook, but it's an important page that sort of gives you some idea of how we come up with these solutions, and concretely relates it back to the precession and to the T2 decay in the Bloch equation. So before I do that, one thing I didn't illustrate last time was just if you go ahead, solve the Bloch equation, all the different parts of it, and then look at what happens. So just look at what happens when you plot the solution as a function of time. So remember, the solution is not going to be the derivative. The solution is going to be the actual evolution of the m vector over time. So it's how does the m vector change over time? And so if we draw our coordinate system here with the x and y and z. So I'll make two drawings. So the first drawing is what happens to the magnetization when you actually do the RF excitation. So that's the first thing. So the RF excitation, the magnetization vector starts off lined up with the field. So that's the m vector. So it starts lined up with the field because a few more of the protons got polarized in the direction of the field, and they're all distributed around the different phases in that sort of cone, so they all cancel each other out, and you end up with the magnetization vector in the z direction. So then you turn on the RF, and the RF is causing the magnetic field vector, the B vector. So remember, the B vector is in this direction also. So it's causing the B vector to wiggle a little bit because it adds some transverse magnetization going around in this XY plane. And the effect of that is to essentially sort of generate a signal by bunching up all the protons so that they actually are sort of precessing in unison, so you get a signal. But if that RF excitation is very short, we can sort of ignore the decay part of the Bloch equation. So the Bloch equation had, the change in magnetization equals this cross product, which explains the precession, and then minus the decay from the T2, and then minus the decay from T1, which has actually got a negative in it, so it's a regrowth. So we can ignore those second two parts, and then what we get is just the basically this vector sort of like going around and around like this, kind of like over the over the surface of you can sort of think of it over the surface of a sphere. And so here's that vector at a moment in time. So the idea is that it just sort of, wiggles around and around and around and around, coming down over the sphere. And I didn't draw it the same length. The idea is that the length doesn't change. So let me just fix that. So the length doesn't change. So here's that same vector. It stays the same length as it sort of rotates down further and further. So it can actually go, that's a little confusing given the initial visualization we had. It can actually go past the plane. So it can start sort of going around like this, and then eventually it can sort of get underneath the plane. So I drew it sort of underneath the plane here. So that's the excitation. Very short, like 50 microseconds or something. 50 millionths of a second, you turn the RF on for just a little pump, and then it does this. So that was the RF brief RF excitation. And for that one, we can use the Bloch equation, but just ignore the second two terms. We just do the first term. So if you just do the first term in the Bloch equation, this is the solution you'll get. And on the Friday graduate session, I'll go over that solution, so you can sort of see how the RF excitation actually, how the solution works. It's a little tricky, so we'll go over that. But basically, all that happens is it just moves down without changing length and just keeps going around and around. So now what we want to do is run the Bloch equation for the relaxation part. So then, this is run the Bloch equation solution for a brief excitation, and now run the Bloch equation solution for relaxation. So relaxation just means, we're relaxed. That's what they call it, relaxation. So it just relaxes. The idea is it just relaxes back to the original starting condition. So here's the starting condition. So what does that look like? So we plotted out separately the equations for T2 and T1. So what we said was T2 decay happens very quickly, and then T1 decay, say we went slightly below zero, T1 decay takes a lot longer. But what we didn't say is they're both happening at the same time. So these two things are simultaneously happening to one vector. So if we try to make a graph of that, what does that look like? So this is sort of like what's really occurring. So there's the x-axis and the y-axis and the z-axis. So what's actually occurring is here we're whipping. Oh, let me draw it in the right color. So here we're whipping around. We turned off the RF, and so the vector is, kind of, going this way. It's whipping around. So, and it's getting shorter. And what's the shorter part? The shorter part is the T2 decay, because T2 decay means reduce the components in the xy direction. That's the meaning of T2 decay. And then this one is T1 regrowth. So those two things are happening at the same time. So, but T2 decay happens much more rapidly, but T1 regrowth is happening. So what's happening is this vector, if we sort of plot it out at various points in time, so here's at one point in time, here's a little later point in time, here's a little later point in time. So that vector is getting shorter and shorter pretty quickly. So just in this is like 100 milliseconds here. So 100 milliseconds, that's, a tenth of a second. So after 1/10 of a second, it's gotten quite small. So, and then it sort of just continues, but it's also growing in the z direction. So it continues to get really small. So it gets really small, and then it slowly grows further and further until it gets back up to the final state. And so then here's your final state, which is, the same as this. So these two things, we sort of conceptually separated them, but they're actually taking place at the same time. So you're getting very rapid loss of the transverse magnetization, and then continuing to slowly point upward in the z direction, and then you get down to virtually no transverse magnetization. It's just 0, and then now it's just these tiny little wiggles, and it's regrowing back into the equilibrium magnetization. And so this is the same, and what is that same thing? That same thing is mz0. And that's, equilibrium mag. Okay, so that's the equilibrium magnetization that you get after a couple seconds. So that was the first finish up from last time, because I didn't draw that. So all we did basically is we just separately got these two equations, the T2 decay and the T1 regrowth equation, but they're actually occurring at the same time. And the precession is occurring at the same time. So all three are occurring. There's precession and T2 decay and T1 regrowth all happening to one vector. So that was the first review, and then the other thing, I'll just leave that aside and just try to get started on the differential equations. So so now let's just try to actually see how we get these solutions that I'm erasing right here. So why is that a solution to the differential equation? And like I said, this is just page 1 of the differential equations textbook, but if you can understand this, then you kind of have an idea of what's the rest of the stuff in the differential equations textbook. So let's just write out the differential equation, just the little piece of it that is the T2 part. So we'll just do the T2 part. So the differential equation, which is just that little piece of the Bloch equation, so throw away the precession term, throw away the T1 term, you just have the T2 term. And so what was that T2 term? So the T2 term was the change in the XY magnetization, and we've also even thrown away the direction of the XY magnetization. It's spinning around, but we don't care. All we want to know is just how big is it. So this is just how big is, what does that mean? This means how big, is change vector. So remember, that's the dm dt vector is like, it's the vector like this that's telling you where the next update of the m vector is. So this guy is the m, and then this guy is dm dt. But we're subtracting out the subtracting out the z component, the change in the z component, and we're also ignoring the precession component. And so what do we want? We just want, what is the little bit of shrinkage in the, going back toward the origin. So that's what this is. How big is the change vector, but just xy part. So how big is the change in the xy direction? So it's important, like you write out these symbols, but they've got this giant, all this information packed into them as the meaning. So that's what this symbol means. How big is the change in the xy direction at a particular point in time? Because that's going to change. The amount of change changes over time. So for a particular point in time, what is the amount of change of the length of the vector in the xy direction? It's decaying. It's, as you can see, like back here, it's decayed to almost nothing. So that's the first part. That's the left-hand side. And now the question is, what is that equal to in our Bloch differential equation? That was equal to the minus, because remember it's a minus, it's subtracted off. So it's the minus amount of m xy magnetization at a particular point in time, not the change in it, the amount of it, divided by T2. So that was our differential equation. So this guy, so how big is the change vector, but just the xy part? This is how big is the m? So how big is the m vector? Not the change, the actual m itself. So it's a very simple equation. It just says, the change in the m vector is equal to whatever the m vector currently is at this time divided by T2. So that's the Bloch equation, differential equation, term 2 Bloch. And then we said we found a solution to that differential equation, and the solution to the differential equation was the following function. And so the function was, so the mxy, so this guy, that guy at the top there, how big is the m vector at a particular point in time? And our equation was the following, which was the mxy at this point just after we turned off the RF. And then that was multiplied by e to the minus t over t2. So this guy is a solution. And today we're trying to figure out how do we get that solution. So this is a solution. So, and this is useful to us because then now we can calculate. This one doesn't allow us to calculate what the m vector is at any point in time. It just says how it changes. This one says, oh, for a particular point in time, like 120 milliseconds, I can just plug it. I plug in what my starting magnetization was, and I calculate this equation in MATLAB, and I find out what the magnetization length is. So that's why it's a solution. So it's not too much. There's only 3 parts to it. So how does it work? So what are we trying to do? So when we solve a differential equation, if you solve, like, here's, y equals x plus 2. Okay, so that's an equation, and we want to solve for x. Let's just do, yeah. So if we have a simple equation and we're just solving for a particular number in the equation, so you could do, let's do not have 2 variables, let's just do, say, 5 equals x plus 2. Okay, so now we have a simple equation that we can solve. And it only has 1 variable. And so we know how to solve that with algebra. You could figure out that that's actually supposed to be 3. So that's kind of what we want to do, except that we're looking for an equation. So here you just find a number, So how do you solve that? You just find a number. But here what we want to do with this case is you find an equation. And what does it count to be a solution? So find an equation whose derivative is the differential equation. So basically what we're looking for is some equation here, some equation that you can take the derivative of. So this says, find the derivative, find the rate of change of this function. That function's unknown. We don't know what that is. That's like the x. So let's find equation. So this thing here is, like x down here. So we have an unknown equation, and so we're looking for an equation instead of just a number. So here we have to find equation. So that's find number, just find equation. And so that's the point. But it turns out this problem is a little more difficult than this problem. In fact, there's multiple equations. There's actually, in this case, there's an infinite number of different equations that are solutions. And so our second problem is find equation that, well, I can put it another way. It's like, where does this mxy0 come from? That's our question. How did we get that? We just made that up. That wasn't in the original equation. And so our real problem is find equation that starts at particular initial condition. And we've added the initial condition. It wasn't in the original equation. The initial condition is, I start off with, 0.2 of transverse magnetization. Now tell me what happens next. Okay, so that's the problem. So let's just sort of go through how we find this, how we show that thing is a solution. And so the way you do solve differential equations is you often sort of try, let's just try a particular solution and just see if when we take the derivative of it, we get our original differential equation. Now, another thing you might look at when you look at this and this, you say, okay, this equation just has a function divided by something and a derivative on this side. This equation has e. Where did the e come from? And so what is e? E is like 2.7, blah, blah, blah. It's the, it's kind of like 2, but it's a little bigger than 2. It's bigger than 2, just under 3. So why e? Well, e has a special property. So what is e? What is this function e to the x? So here's this is x. So e to the x. So if we just plot out e to the x, what does it look like? Well, it kind of looks like this. It goes up and up. It's an exponential function. So this is e to the x going that way. And this is x going that way. So it turns out e to the x has a very special property that if you go to some point on the function and then find the slope, also known as taking the derivative. And so what is the slope? Well, the slope is like, for a given amount going in x, how far did you go up? So that's the derivative. And you look at the value of that slope. The value of that slope happens to be equal to the value of the function. So if the function at this point was like, say, 1.5, something like that, then the slope would be 1.5. And so this is a special function whose whose derivative, i.e. slope, is always the same as the value of the function. So it's a kind of a special function. So what does that mean? So that means that if we take, here's e to the x, and if we take the derivative of that, often just written as to sort of not have to write out dm dt, we just write an apostrophe like that. That's the way a mathematician would often write the derivative. So the derivative just equals the function. So that's kind of a handy function. And if you look at this equation, that equation is like that. It says the derivative of a function equals the function. There's a constant in there too, but it just says derivative of the function equals the function. So this might be a good one to try. So that's why you end up when you're searching around for solutions to the differential equation, that's how the e got in there, because it happens to be a special function that has that property. Okay, so let's start by just showing, first we'll find one solution. So I'll start with the differential equation. So I'll write it in with slightly smaller number of symbols. So here's the differential equation. So it's the derivative of this function. That's just a way of writing that in smaller number of symbols. Is equal to, and then we'll take the constant out. So it's equal to minus 1 over t2. That's just this thing here. Times the function. And remember that function is the unknown function. So this is the differential equation written in a smaller number of symbols. So the derivative of a function, unknown function, is equal to this constant times the function. So remember, this is the unknown instead of x. So we're saying, like, we're looking for a function, not just like a number. So so when you look at that, like I said, what it says is, derivative, equals constant times function. So derivative of function equals constant times the same function. So here's one solution. So just one solution. So one solution is, so here's m as a function of t. So there's no derivative on that now. It's like this guy, it's an unknown function, but now we've solved it. And when we've solved it, our answer is e to the minus t over t2. We could also, write that out as, just to make it a little more explicit, e to the minus 1 over t2 times t. Okay, so e to the power constant times whatever the time variable is. So how do we show that that's a solution? We show that that's a solution. We take the derivative of it. Take derivative to check. And what do we want to check? We want to check that if we take the derivative of it, we end up with, with our original differential equation, which says the derivative of some unknown function equals a constant times the function. So now we have to take the derivative. So you probably forgot about taking derivatives, or maybe you never took taking derivatives. But when we take the derivative of this function, what do we have to do? We first have to take the derivative of the power, and the derivative of the power, it's the power t is t to the 1. It's not like t squared, it's just t to the 1. And the way derivatives work is if you have something like that, you reduce the exponent of the variable by 1. So it goes from 1 to 0. And when the exponent is 0, then that just means it's equal to 1. So that just disappears. So you just end up with a constant. So if we take the derivative of this function, we just get the constant, so minus 1 over t2. So that's this guy, derivative of constant, derivative of exponent. And then the rules of derivative are that we first take the derivative of the exponent and then we multiply it by the whole thing. And so then we multiply it by e to the minus t over t2. So, which is that thing? That's the same as that. So, have we gotten the correct answer? And we have, because if we look at this thing right here, this thing is equivalent to this function. We're just substituting it in for that function. Same. So that shows us that when we take the derivative of the function, we end up with the correct answer. It's the same as mt. So this thing is the same as, sorry, not that thing. This thing is the same as that guy. There's lots of substitutions in here. So when I take the derivative of our solution, what happens is I get a function that is the same as our unknown function. And so that solves the problem for us. So we find an equation that when you take the derivative of it, you get the differential equation. So we get back to our differential equation. So the derivative of it is correct. So that's a very simple case where we just take the derivative. I mean, it's basically just this. We just take the derivative of e to the x and we get e to the x again. But that's just one solution. So it turns out there's a whole bunch of different solutions. So let's take another one. So if we take another one, so this is one solution. So this is another solution. So another solution is here's our solution to the differential equation, and this one equals some other constant. So I'll just write it as const. So say it's 2. I'll give an example of what it looks like if you draw it out for 2. So now instead of just a solution where our xy magnetization as a function of time is e to the minus t over t2, let's just say it's some constant, like say 2 times e to the minus t over t2. So now let's test that. So take derivative. So that's one solution. So let me put one more green line in here. Okay, so there's the differential equation. Here's one solution. Take the derivative to check. Here's another solution that has a constant in there. Let's take the derivative of that one to check. So So when we take the derivative of that one, we're going to have to, it will be similar to what we did before, where we'll first, pull out the exponent, take the derivative of the exponent. The t goes away, so we just have the number multiplying the exponent. But this time, when we multiply, the thing we multiply by is this whole thing. So the whole thing is going to have to go in there. So there'll be the constant in there, 2 times e to the minus t over t2. So why is that constant in there? Well, just think of a very simple derivative. Like, what's the derivative of 2x? The derivative of 2x is just 2. So that's kind of what we're doing here. So we have to take the whole number, like the 2. That you can sort of think of this thing as the 2 in the derivative of 2x. So have we solved the equation? Yes, we've solved the equation again because this thing is equal to this, which is equal to the function. So basically we've gotten back to our differential equation. When we take the derivative of this thing, which is that, we end up with the same thing. It's just because the m could either be just e to the minus t over t2, that's the unknown function, or it could be any old constant times e to the minus t over t2. That would work there too. So the bottom line is that a differential equation, is different than this kind of equation. So in this kind of equation, we just solve and we just find x equals 3 and we're done. A differential equation is kind of weird. What it is it just says these are the constraints. These are the constraints. Like whenever you take the derivative of the function, it's going to be equal to this, which includes the function. But it doesn't tell you what the function is. And in fact, there's an infinite number of different functions that would solve this differential equation. So it's less constraining than this kind of equation where you just have x equals 3 and you're done. So that will show where this initial condition comes from, because the initial condition is the constant. The constant could be anything. So let's just draw these equations out now, just so you can sort of see what they look like. So if we just make a little space for myself here, not erase anything too critical. Okay, so if we just draw out this, make sure I can, here's the edge, I can see it there, don't go past that. Okay, so if we have a 0 here, and here's the function. So what we're plotting is, we're plotting our various functions going this way, and then time is going this way. So let's start off with the first one, which was just e to the minus t over t2. Let's just plot that. So if we plot that, when t is equal to 0, e to the 0 is 1, and so that's where the equation starts. And then if you plug that into MATLAB, it would just be like exp of t divided by t2. Plug that into MATLAB, and then plot as a function of t. What you just get sort of a nice. Let me put the 1 down a little bit further. Sorry. I need to go up to 2. Okay, so that's going to be 2, and here's going to be 1, and this is mt going up that way. So if we plot that guy, what we see is it just sort of falls off like an exponential decay does. So that's this equation here. So that's this guy. Put it in red. So if we plot this guy, it's going to go up there. Okay, but now what if we plot this other one, which also works, which is any old number times e to the minus t over t2, also works as a solution. So let's, for example, 2. So if we plot that equation starting at t equals 0, t equals 0 is e to the minus 0, which is 1, times 2. So that one starts off at 2. So this guy starts off at 2. And it will just sort of go down like this. Didn't make it go down quite enough. So it'll just be 2 times that other one. And just go down. So that's also a solution. And in fact, we could start off at, t equals, minus 0.5. And what you would get is you would get something that sort of went up like this. Or you could start down here, or you could start, higher, anywhere in between. So essentially there's infinite number of different equations. So if we plot this one for just put the whole thing, yeah. If we plot that equation for constant being 2, we get that equation that's twice as tall. So how does this work? Well, the way this equation works, what does this equation say? It just says the rate of change is proportional to, T2 is the proportionality constant. It's proportional to how much is left. And so if you're, say, at this point here, a little beneath 1, then it says you're gonna drop that much, proportional to, say 0.6. But if we start at, say, 1.5 or something, we're going to drop twice as much because we've got, this this number here is bigger. We're starting off with a bigger amount, so the drop is bigger. And similarly, there's a negative sign, so what happens if you start off negative, you'll actually go up. So this is just a very basic differential equation that describes some process that is dependent on how much is left. So there's a lot of things like that. Some water's running out of a, running out of a little container. As the water goes down, the sort of the pressure pushing out of the container gets less. There's many different things that happen this way. Or the predator is eating a prey, and as they keep eating the prey, there's sort of less prey left, and it gets harder to find them. So there's zillions of physical processes that depend on the amount that's left. So this says, the change is equal to the negative of the amount that's left. The negative is important because that's why it's always going down. So that's the bottom line. So the bottom line is that this initial condition is that unknown constant, and that's some additional information that we've brought into the equation. So the initial condition is like how much XY magnetization is there after we start. So that thing is, where we start on this equation. So it tells us, we start here and then here's what's going to happen. Or we start here, here's what's going to happen. So that initial condition allows us to sort of add in some information that wasn't in the original differential equation, which is however much magnetization we're starting with. And that's useful because, we might be starting with different amounts of magnetization. So basically when we, plot out that function, we're starting from a number that's, the mxy just after we turned off the RF pulse. That's where that number comes from. That's an initial condition. It's not actually in the differential equation. We've just added it in. So here's our initial condition. Okay, so I think the plan is to end the recording here, and then we can have some questions about this, because this is, if you haven't done this before, this is quite sort of disorienting to sort of think of an unknown as an actual equation. So you're looking for an unknown equation instead of an unknown variable that just has a number as an answer. So, but like I said, the bottom line is we're just trying to figure out, here's our differential equation, which is the Bloch equation. And what we're trying to figure out is, why is this a solution? Where did that solution come from? How did we get from here to here? Where did the mxy 0 plus come from? We just tacked it in. It's this initial condition. It's basically this constant here. The constant you can stick in any old thing, and we'll get a solution. As long as the solution has this part in it. It has the e to the minus t over t2. Okay, so I think we'll end the recording, but keep the Zoom session up. So it's good to end the recording, David.